Stat 201.
Hey Brian, what's up?
Hey Adam.
Oh, what's this?
Adam, what are you doing? Adam!
No!
Hey everyone, Jason here. We've tried to find someone to do the Kahoot. You know what though? We could just try and bring him back. I happen to have this. So we'll see what happens.
I missed the transition a little bit there. Good to see everybody. I was sending out messages. I think people got the message. I see people in the chat. Wow, a bunch of people showing up right there. Mewbots in the chat. How's everyone doing? Megan, good to see you there. Riley, insane good to see you there. Jaden, Caitlin, Darius. Had to switch accounts. No worries. Good to see you there. How's everybody doing? We'll get started here. What chapter should we do? We'll take notes on it and start reviewing the content. We'll create some questions and multiple choices. What should we do? You pick it. Chapter 7 is regression. Chapter 18 is regression wisdom. Chapter 13 and 14 are sampling distributions. Let's go 13 and 14. Wrong button. Okay, chapter 13 and 14, sampling distributions. So let's start with chapter 13 right here. So we're at the 344 mark. And test 2 review. And chapter 13, sampling distributions. Okay. So it used to be that this was just chapter 13 and then they split it up, but we like that chapter 13 is sampling distributions of the proportion and chapter 14 is sampling distributions of the mean. Unfortunately, the chapters also have confidence intervals in chapter 13 for confidence interval for the true proportion and chapter 14 confidence interval for the true mean. So they used to split it up differently, but we've kept the way that we had the book originally split up. Good to see you there, Joshua and Jaden. So we're planning on doing the review, right? Because here's the thing. When you get to the test, what should you look at when solving a chapter 13, 14 problem? So this is your, know this right now. Pro tip. Fill this in for me. When solving a chapter 13 or 14 problem, always be looking at the what? What should you be looking at? And then help me go there. Mewbot will help you go there. What should you be looking at? These are things you should know. Yeah, you want to start with that? Great job, Bella, right there. You know if it's cat or quant. Bella, let me throw you some points. Totally perfect answer right there. And where do we then look at to see how to do these problems? It might be Darius, and I'll be talking about that. Darius, good point. For proportions, it is in percentages. And we'll be doing that here in a second. We'll be doing a chapter 13. I've got chapter 13 marked right now. So what do you need to be looking at? You will look if it's cat or quant, but what should you be looking at to see how to solve these? You should be looking at your what? Which you get this on the test. You get to use this tomorrow night. What do you get to be looking at? You're like, I need to print this off now. I need to be looking at it. I need to know what that information says. The formula sheet. Thank you, Riley, right there. And Bella, you need to look at the formula sheet. And so you need to look at the formula sheet. Make sure you know the formula sheet. We're going to start off by looking at the formula sheet right now, and you should know every bit of notation on that formula sheet and be able to come up with example problems for it. The only way you get this down is by just practice and memorization, and then you can solve the deeper problems. The formula sheet is found under the exam 2 review page. Right here under the formula sheet. Mewbot's got the link in the chat for it right there, and we'll make it the pinned link so people can come back and see it. Now, does everyone see where we're going for chapter 13? Where's chapter 13 on this page? Where's chapter 13? If you're looking at this page, where's chapter 13? Where the heck is chapter 13? It's all the proportion stuff. Great job, Darius, on fire right there. We like it. So this is chapter 7/8 with regression. This is chapter 12. Oh, wait a minute. It's probability. Which one's that? Is that chapter? I think it's chapter 12. And this is 13, and this is 14. Sorry if that's chapter 10. I think chapter 10 is sampling. So correct me if I'm wrong. Chapter 12, I believe, is probability. They're numbers. But 13, 14 down here at the bottom are going to be very important. So let's go ahead and grab just chapter 13 and see if we know everything we have. Okay. So what I need from you in the chat is to tell me any. So next tip. This will help for exam 3 even. Know all the notation and give examples. So tell me something on this screen. Any of these things. Any of the notation. Be careful because there are mistakes to be made. Because you'll be like, well, but you've said this. Maybe the first one's a tricky one. And if you don't know it, just say, Brian, what is this? You got it, Brian. Well, we can do some of that here. I'm dedicating this one to doing the test. So you need to know the notation. Help me out here because I can say them all. I've said them all a few times. So what is any of the notation here? I'm probably not going to use my pen. I'm going to write them because my handwriting is so bad. So what is any of the notation? What I'm asking you for is anything up here. So what is p hat though? You got it, Darius. What is p hat? We need to know what p hat is, and we need to know an example of it. So let's put p hat right here. What is p hat? What is p hat? Darius is on the right track right here. We have to put what p hat is and an example of it so we could find it in a problem, because a problem might say p hat, or we have to find p hat. What is p hat? Oh, got some good stuff here. Sample proportion. What is the formula for p hat? What is the formula for p hat? What is the formula for p hat? X, Darius is on fire. X over n. X over n. And so X is lowercase x technically. Amount of successes. N equals number of trials. We overcomplicate these things. Great job, Jackson, too. We overcomplicate these things because you know how to get p hat. 10 out of your 40 friends own snakes. What's p hat? 10 out of your 40 friends own snakes. 10 out of your 40 friends own snakes. What's p hat? It's a biased sample, but 10 out of your 40 friends. Sure, number of successes. That's it. That's all it is to it. So that's the sample proportion. And you heard a problem right there. We say you sample 40 people. Friends, I said, but you sample 40 people. 10 of them own snakes. That's considered a success. That's what p hat is. Now, if we find p hat, we don't really use it in these types of problems. What else can we find if we know p hat? What else can we find if we know p hat from p hat? We won't really be using it for this chapter. It'll be very important later on. It's not used in the notation here. But if we have p hat, what could we also get instead of p hat? What could we also get? I'm giving hints. What could we get if we know p hat? So we're marking all the notation here. The formula for it's 1 minus p hat. It's the complement of p hat. So what can we get if we know p hat? Q hat. There you go, q hat. So what is, if p hat is 0.25, what is q hat? In this example, because I'm trying to do examples right here, like 25% of your friends own snakes. What is q hat then? And then what does that mean? Because it's the complement. It's like the not group. So 25% of your friends own snakes. What's q hat? 25% of your friends own snakes. What's q hat? There you go, Kai. Great job right there. So there it is. It's just the complement. So you just do 1 minus and get the answer. I need more notation. Don't worry. I saw some answers that were a little iffy, but give answers, more answers. We've only identified so far the following. We've identified, we haven't done P yet. We've done P hat. We've done N. That's all we got here. So we got a lot more to identify because we have to know what the notation is to be able to solve these problems. We have to come up with examples. So if we're reading a problem, we know it says like out of a sample size, expected sample proportion equals P. So literally, Darius, man, you got some great knowledge right there. Amazing work. Darius says that what we have, and then you can tell me what P is also if you want. Darius is talking about mu mu p hat. Mu p hat. Where's a mu in here? Mu of p hat. And this is a full phrase. Really? Is expected sample proportion. So that is what percent you expect to be burned. For example, the cookies. Yes, given your mom burns 20% of cookies, you'd expect in a sample to have 20% burned. So this is the expected sample proportion, the mean of the distribution. So it'll be put at the center. And what is it equal to? It's equal to P. So what is P? And then I'll do some more examples with this. What is P? P stands for the what? And then we'll make sense of this with talking about it a little bit more. What is P right here? What is P? P stands for what? Because Darius is right. This is the expected sample proportion. But what is P? So we're doing pretty well. We've identified what this is. This is a full phrase. The full thing needs to be talked about. It's not true mean sample proportion, which it looks like. Close, Kaya. Good work. Very close. It is actual, but since it's the actual, we're going to say the true proportion for the population. So that is the true population proportion. Is not for the sample. It's like for all the data. So over the history of your mom making cookies, over every cookie she's ever made, she burns 10%. So how many in a sample would you expect your mom to burn? What percent of a sample would you expect your mom to burn if your mom burns 10% of cookies? So if P were to equal 10%, like your mom burns 10% of cookies. From all the cookies she's ever made, you have data on all of them. She's burned 10% of cookies. So if she were to make cookies today, you would expect this sample to what? This is what it means. Like you look historically at the data and you say, she burns 10% of cookies. So you know the truth because you know your mom burns 10% of cookies. So P, that would say you have witnessed over the long run. And so, but say to me as a sentence, if my mom burns 10% of cookies and she makes cookies today, I'd expect in the sample of cookies what? So if you know your mom burns 10% of cookies and then she makes cookies, you would expect in that sample of cookies what? And think how it's expected sample proportion and it's mu p hat equals P. The expected sample proportion of cookies burned from a sample of 1,000 cookies, you make a lot of cookies, is what? Well, it's just equal to 10%. Because you would expect your mom to burn 10% of cookies if she historically burns 10% of cookies. Not saying she will, because that gets us into another concept over here. What is this? And then we're almost done with this. And then we'll do an example problem here. So let me mark that this is notation. So what is that thing? What is that thing I just highlighted there? What does that stand for? We're almost done with notation. Then we do a practice problem. What is that thing? Any guesses? Yeah, exactly. In a sample, I would expect 10% of a sample to be burned. I have no idea why it's doing that. What is that thing? What is SDP hat? Any guesses? Really? What is SDP hat? SDP hat. I don't want it to indent it. I think it's because I haven't indented. Everything was going so purty. SDP hat, does anyone know? I'll say it in a second. SDP hat. There we go. The standard deviation of the sampling distribution. Great job, Kaya, right there. The standard deviation. So standard deviation of the sampling distribution tells us variation. We'll see this in a moment because your mom's not always going to burn. Are there any other person? There might be. Check out the announcements. We sent out some of them right there. Moira also sends out announcements. So check those out. I think Moira has been sending out like SI announcements and she'll announce them in class a lot of times too. So, and then we have the online reviews also. The standard deviation right there. SI exam review 2s. There is one on today's the 7th. Yep. Check out the announcement, SI exam reviews 2. So, and I think they're doing it They've got it listed here. Mossman 212. There it is right there. There is the Hayden's doing tonight. There you go. Pause the screen here. Would this be, it is the variation. Exactly. It tells us the variation. What is the only thing? Yeah, Moira is awesome. What is the only thing we haven't mentioned on this screen? What is the only value we haven't mentioned, which is very easy to solve? What is the only value we haven't mentioned? The only value we haven't mentioned, and then we'll have all the notation done. And then Q, easy. 1 minus P equals Q. So Q is 1 minus P. And we just, oh, we haven't done ZP hat. So ZP hat tells us how odd, I don't know why it keeps changing my format on this thing. There we go. Z sub P hat, I can do it this way. Wonder if I can drop this right in here. ZP hat, the z-score of the sample proportion lets us know how odd it is. Could you please send the link in the chat for Hayden's review tonight? I don't drop those out. Virginia, you're on our class, right? Go to the I'm always afraid to put links that go to class type things because these are public videos on YouTube, as the syllabus says. But you'll see the announcements, SI Exam Review 2s, and it should have it right there. So check it out. Here it is right here in the chat, the place, and the link is there over on Canvas. Thank you, Virginia, for asking. Good questions. So with this right there, we have all the notation right here. Who's ready to solve a problem? Let's see if you can solve a problem that would step you through each part of this. Okay, test 2 review. Nice job, Darius. Chapter 13, practice problem. Okay, so I need everyone's help on this because I want to see how much of it you can get. So a company knows that exactly 4% of their products are defective. They have made millions of products over the last few decades. They take a sample of 400 products and want to know if and find that 6% was defective. Is this odd to see? 1. Check all conditions and state in a full sentence if we pass or fail the conditions. 2. Find the mean of the sampling distribution. 3. Find the ST of the sampling distribution. 4. Find the sample proportion. 5. Find the amount of successes in the sample. 6. Was the sample unusual? Give a value that justifies. Okay. Who can help out with the first step right here? Check all the conditions and write them in a full sentence. So what is the first condition we have to check? For the remainder, great job, Darius, and got into good order right there. So what's the first condition we always check? Do we pass it? What's the first? I think you saw the first condition. And do we pass it? The first condition and do we pass it? Random. The question states we took a random sample. We're good. Condition 2, this is where you keep going. So what's condition 2? Darius has kind of said it, but talk to me about condition 2. I want a full sentence on it with justification to show me you know how it's met. So random is met, I'll put them right here. Random met by saying it was random. I need condition 2 now. I do them in this order because it's just easier to remember from this chapter forward that they're always the first 2 are the same. The third condition will be different depending on what data we're working with. So what is the second condition, and do we pass it? Don't worry about being wrong. Just take some shots at this. If you get it right, awesome. If you get it wrong, it's just practice. So what's the second condition? The second condition is, and then do we pass or not? So Darius has got it right there. It's the 10% condition. And check that n over n is less than 0.10, which is 10%. So you want to see that we sample less than 10%. So do we pass it? Yep. Boom. Ryan on fire. That's perfectly what I want. It's way less. Like I said, millions. Like you only sampled 400 out of the millions. So we definitely pass it. We are totally fine on that. Now, what do we do before we say the next condition? We pause. Because you might be right, but you might be wrong. Everyone's going to want to say this condition, and it might be right. But what's the next condition? For this test right here, what is the next condition? Good question. So the n is the sample size. So you have n sample size of 400 out of the population size millions. So right there. And it's capital N technically because capital N is population size and is sample size. We didn't mention capital N on our notation sheet. We probably should have, but capital N is the population size. How many total have they produced out of everything? And then N is the sample size. So right there, Ryan did the math. 400 over millions is way less than 10%. So we've sampled way less than 10% of the population. So what's the third condition here? Really good questions. What is the third condition? This is when we pause and you have to be like, wait, what's the third condition? And then how do we check it? How do we check it? Success, failure. Yep. And it's because it's categorical, which someone said earlier, when you know if we're doing cat or quant. So that's not a condition. That pause is not a condition. That's just being like, is this categorical or quantitative data? Since it's categorical, we're doing success, failure. If it was quantitative, we would do large enough n. Success, failure. What does it state? We need NP and NQ both greater than 10. So what is P? What is Q? Great job. Poison for the cat. Dylan, good to see you, Dylan. What is P and Q here? We've already identified N. So we have to solve both of these. What is P and Q? So you see a lot of this boils down to notation. What is P? What is Q? So if you throw me P, I can find Q. Be careful. You'd probably get this right even if you made a mistake. Exactly. The company knows that exactly 4% are defective. So that makes that P because they know it. So realize that if they know something and it's a truth, then it's the true proportion for the population. And then Q is found by doing 1 minus P. So do we meet the condition right here of NP and Q both greater than or equal to 10? What are your thoughts on this? Do we have NP and Q both greater than or equal to 10? It'd be 4% of, yep, great job, Dylan, right there. That is correct. And I'm trying to, good work. If you see the highlighting, I'm trying to show it via highlighting also to show that we are being able to check these and mark the notation, which, as I said to start, really boils down to notation. So you'd have right here 400 times this. Who thinks we meet it? Do we meet the condition, yes or no? Once I hit this button, the question will be answered. 4 times 4, move decimals around. Yes, we meet it, 16, there we go. So do you know what NQ is? It's 384. What do NP and NQ add up to? If you find NP and NQ, NP and NQ add up to what? What do you notice? Exactly, it's the smaller one, Dylan, right? I mean, Darius, sorry, Darius. What do you notice NP and NQ add up to? They have to add up to this because it's like, well, if 4% are bad, 96% are good. So if you add the two numbers, NP plus NQ actually equals what? It's always the case that NP plus NQ equals N. P plus Q equals 1. And so basically, you're just timesing N by 1 and you're adding it up in parts. Does that make sense? So NP plus NQ equals N. It's just a fun fact that when you add those up, you will get the total sample size. And it actually answers a later question. You'll see that. Equals your sample size. Great job, Darius, and good practice, everyone. What is the mean of the sampling distribution? What is the mean of the sampling distribution? Who knows what the mean of the sampling distribution is? So when you're working these problems, you need to look at your formula sheet. You need to look at the formula sheet because this question is super easy. So what's the answer to the mean of the sampling distribution? You might have to scroll up. What is the answer to the mean of the sampling distribution? It's asking, when it says the mean of the sampling distribution, it's asking for this quantity. It says, what is the mean of the sampling distribution? So it's asking this. So what's the answer? Yeah, William got it. That's it. It's just mu p hat equals p. And thus, we just literally have mu p hat, the mean of the sampling distribution. The expected value, the mean of it, is equal to p. So it's just that, and it's all the way up there. There it is right there. Expected sample proportion is p, right? So it'd be that. What is the standard deviation of the sampling distribution? I think we can get it all. Just is that, tell me if it's too small, but that keeps it on one page. What is the standard deviation of the sampling distribution? So it's literally asking, what is SD p hat? And that is equal to something. Go ahead and try and solve it. Let's quote 191. A lot of this comes down to just knowing your notation. What is SD p hat? It's p times q over n square root. P times q over n square root. P times q over n square root. And that is equal to 0.04 times 0.96 over 400 quantity square root. Make sure to do the quantity. Ooh, Riley. Riley, how about we round that to what? Ooh. Oh, man, this turned out weird. You know what I'm going to do? I'm going to change the this thing over here to 8 for science. Wow, Riley. Because is a product defective? So really good question, Dylan, right there. So a company knows that 4% of their products are defective. So when you ask the question, how would they collect the data? They'd have to look at the product and say, is it defective or not? Which is that cat or quant. Cat being categorical, quant being a quantity. So the reason we're going with this is because when we ask, is a product defective? That is a categorical question, and categorical questions deal with the proportion. Proportions for qualitative, yeah, I hate the word qualitative, starts with a Q, but that is correct. You are correct, Dylan. Let's throw you some points. Proportions are for categorical, qualitative data, and the mean is for quantitative. You are correct. The next one says, find the sample proportion. I did just change it. So what is the sample proportion p hat? What is the sample proportion p hat? What is the sample proportion p hat? It's just listed. I did change it, so... change it for science. What is the sample proportion p hat? Anyone know it? What is p hat? It's in the question over there. So we're trying to find p hat. P hat equals x over n. It's not the mean though. Good guess, Dylan. It's what they saw in a sample. So that question says, what did they see in the sample? Like, it says, what was the sample proportion they found? And so what did they see in the sample proportion? Yeah. When you see it, you'll be like, oh, yes, it says it. What was the sample proportion? I've overcomplicated by writing x over n. A lot of people do this. They say p hat is x over n, then they start overcomplicating it. Not 400, good guess, Dylan. That's the sample size. So that right there is the sample size. So what was the sample proportion? Proportions are numbers between 0 and 1. That is the true proportion. That is what the truth is. So that says they know that 4% are defective. Like from their data, they know 4% are defective. That's the truth. That's the truth, though. 0.04 is the truth. We got it. It is p hat is what they see in a sample. Who gets this right here? That it says right here that they took a random sample, and in that sample they saw 8%. It was 6%. Anyone type 6%? I did change it for reasons. I didn't like the z-score, and I wanted it to be a little more different. So I changed it for that. If you're saying 6%, you're probably right because I changed it. It is 8%. So the next question is kind of a play on this. Sorry, Jackson. I'm so sorry. You can keep it. You'll see what the z-score is, and it's kind of like an iffy z-score. It's kind of like, well, that's a little weird. I wanted the z-score to be very weird. Find the amount of successes in the sample. The problem doesn't give this, but the answer is 32. How did I know this? How did I know there were 32 successes? And how could I check my work? The problem doesn't ask this, but I don't know how many we've asked on the test, so don't freak out over this one. But the amount of successes in the sample is X. I'm just doing it as a review question. It's Dylan. I like it. And that is N times P hat exactly. Or you could do, there's like, you can just check with 32 over 400. It's just a check your work problem. And you should get 8%. Like if the successes in the sample is X, and then you could also take the percent that were successes in the sample, 8%, and times it by that. That's not how we do the NP-NQ condition right now, but that's just a good check right there. And you can just plug 32 in, or you could literally just times both sides by N. Do you see, if you times both sides by N, you will get X. You'll just math out the X. So that is just a way to solve for X right there. Not a big important problem. Let's get to, was the sample unusual? How do we usually justify if something is unusual? We usually give someone a what. To justify if something is unusual, we usually give someone a what to justify this. We would say like, well, let me give you a this. To talk about the context if something's unusual. Z-score. Dylan knows right there. You got it, Dylan. Z P hat is equal to P hat minus P over P times Q over N square root. And so we just plug in the numbers. Literally from our problem, we have 0.08 minus 0.04 over 0.01. And these were all solved previously. Like this right here is P, and P is this value right there. It's still the same thing. And so that value gets plugged right there. You can see it up there also. And then down here on the bottom of the equation, trying to find a different color. We got this color we haven't used yet. This color right there, which solved out to this, which is the same thing as this, solved out to 0.01 right there. And then the 8% solves right there. It's literally just plug in the numbers. Exactly. And so what does the z-score solve out to right now? The z-score solves out to what? Pretty easy z-score to solve. I rounded the decimals. Wait till the end of round. If you do it exactly, Riley gave the exact. So if you do it exactly, you'll get 0.08 minus 0.04 divided by this. And there it is right there. 4. And it might be some rounding. Riley's done all the exact math. So it should be about 4. And is 4 unusual? 4 would be very unusual here. So it's very unusual. The previous one that I didn't do that I changed would have solved out to basically 2. And 2 is kind of on one of those iffy things. I don't like when the z-score solves to 2 because it's like, well, it's kind of weird. It's not super weird. I wanted something to be unusual. And if we draw out the distribution right here, you'll see that the 8% is off the scale. You put the 0.04 right here, or we could do percent, make the numbers easier, right? 4%, 5%, 6%, 7%, and 8% would be over here off the curve. So our observation of 8% is off the curve and very unlikely. Does that make sense? Yeah, 2 is kind of one of those iffy, like, well, it's a little high. It's not that high. Usually it's outside of 2 and negative 2 is kind of weird. Outside of 3 and negative 3 is very weird. Outside of 4 and negative 4 is extremely weird. So it's like, when you think about z-scores, 1 is common, 2 is weird, 3 is weird, 4 is super weird. So it gets weirder and weirder the further out you go on the curve, like more unusual, excuse me. Like, if you were to color it, it would be like pretty normal to see, kind of odd, a little large, very large. And once you reach past that, it's just ridiculous. It's subjective what people call these things, but everyone would agree that z-scores, the further out you go on the curve, the more extreme they are. I usually think of 3 as an outlier. 2 is like a light outlier. It's not like 2.9 is definitely weird. It doesn't just become an outlier magically at 3, which is my problem when people are like, 2.98 is not an outlier. And I'm like, it's pretty weird. Pretty weird. Just the further out it is, the more weird it is. A z-score of 1.4 would not be unusual. A z-score of 1.8 is not really that unusual. 2.3 is kind of unusual. 2.8 is pretty unusual, like pretty darn unusual. 3.4 is like, whoa. Well, you can do the z-scores for a lot of things. And this was so the answer was this is very unusual. The z-score is about 4. That's pretty darn unusual. It's way off the curve over there. So you're ready to do some chapter 14? Who's ready for chapter 14, which is very similar? We got some I'm raised in the chat. We're going to do the notation review and then do a question. I thank everyone for being here. Test 2, Jackson's got this. Chapter 14, sampling distribution notation. Yeah, doing some errands right there. William's got it. Taylor's ready. Okay, so you know the first thing we're doing? What should you know back and forth? Say it with me again as we're about to go grab it. You need to know this well. You got to know what's on this. And for the next test, you have to know what's on it. If you don't know this, you're going to have a bad time.
Notation,
You're
brother.
gonna be like, I don't even know where to start. You need to know that notation, brother. Okay. So here we are. You have to know notation. You have to know what all this means. Tell me what anything means on the screen. There's a lot on this screen. What does any of it mean? Just start me off somewhere. There's some easy things. This is your time to see what you know or don't know. Don't worry about getting it wrong. We're also going to do a practice problem right after this, but just try. You have to be able to think of like examples of these. Expected population mean. Darius just on fire. Walking and doing errands and perfect answers. So the expected, let's write right here. I'll write mu y bar. Expected sample mean, Darius. Expected sample mean is the population mean, the true mean. So it's expected sample mean, which is y bar, which also clues us in on something else. Darius, really good work right there. Expected sample mean. Just small correction. That's a pi. Yeah, good work. We read the mu right there as expected, and then y bar is sample mean. So expected sample mean. And so this is equal to expected sample mean. And the way this works is if we, is the true mean, and we could just maybe put like equals mu, and then we'll put after this. And so this is the phrase, expected sample mean is the true mean, making mu equals the true mean for the population. It's weird. Don't try to read mu y bar as true mean of sample mean. This is the mean for the sampling distribution, what we put at the center. It's what we were doing just a second ago. We literally put mu p hat at the center of that curve, and this curve will have mu y bar. So it's the center of the sampling distribution, what is expected. And it's not an error. And so now, any other notation, help us out here. What other notation do we need here? Because we've only done the following. We've marked this. I'll try to mark everything as we say it. These different colors. So that's a different quantity. Remember that. That mu is not the same mu. Standard deviation y bar is standard deviation of a sampling mean divided by the square root. It's that pretty much. Douglas here, I'll break it down. Douglas, you got it. So we got SDY bar. So SDY bar is going to be equals the standard deviation of the sampling distribution. Tells us expected variation around the mean of the distribution. Like it tells us the spread. We saw that just a moment ago in the previous problem. And the true mean is just like a fact. Like the true GPA of UT students is 3.5. And that'd be a fact. So now if we took a sample, we'd expect the sample to have an average of 3.5. Not saying it will. It'll have variation maybe. What else do we have on the screen? We've kind of marked a lot, but tell me something else. We've marked a good bit now. We're getting close to almost done. We only really have 3 more things to mark. That's SDY bar. It's a full phrase, hence why I'm not breaking it into parts. So what else? Yeah, you've done really well, Douglas. What else do we have? We have 3 more things to mark. One of them's really, Douglas basically gave us one right there. Nope. 3 more things to mark, and then we get a practice problem. 3 more things. What are the 3 other things? Surely someone knows what that is. That one we use all the time. Then we have two more things. Close, Dylan. Good guess. It is sample size. That is sample size. Sample size. Good guesses. Good guesses. This is sample size. And then, and I think Nick right there. Which one are you talking about, Nick? Because I think I know what you're talking about. Nick says population standard deviation. What is that? Population. What symbol is that? Population standard deviation. Where is that? Sigma. You got it. Good job. And then we have one more. What else do we have? Tell me the last thing on here, and then we'll get it on here. Take these notes if you don't have them already. Where's my sigma? Where's the last one? Sigma. Okay. Population standard deviation. The last one. What's the last one? Pretty easy because we've already marked this whole bunch. Ooh, we haven't done that yet. Oh my gosh, I'm saying last one and I'm wrong. There we go. Really. Nick, good job. And this is sample mean. And then y bar is the z-score telling us how odd our sample is. It's the z-score of the sample mean. Zy bar is the it's this. It tells you how odd your sample mean is. So the sample mean would be like from a sample we saw a GPA of 3.3. Population standard deviation is the population has a standard deviation of 0.3 or so. Sample size, we spoke to 100 random students. So I got some examples on here. I'll just leave the screen up for a moment, and pretty much everything's marked. But any questions on this before we do an example question? You want to be able to do as many example questions as you can. You should know where the notation is at, know how to find it, be able to solve these types of questions. Because really, I can't say it enough, it really boils down to notation. It boils down to knowing what each of these mean, and then you just plug in the numbers and solve it. I mean, it's easy when you know the notation. It's very hard when you don't. So you have to know what each of these mean and know examples of it. Okie dokie. Let's do a problem right here. So let me mark this in the notes. 44, 54. Test 2 review. Chapter 14. Practice problem. Okay, well, we have to label all those. Not really label. We do ask questions that are like, what is this in notation? There are some easier kind of not high-level questions. It's easier when you mark them, Riley. It's way easier when you mark the things in the problem and you know it. And you can just write down your notation. You're like, well, I can solve this. S99 Mossman, I believe so. Double check the announcements. That does sound correct. Okay, so here's the problem. I'll make sure to get those notes down. Yeah. New computer this afternoon. Oh, no. Sorry to hear that, but glad you got a new computer, Darius. Like, that's awesome, man. New computer's always nice. Sorry to hear that, though. We know that the average student spends $60 a week on groceries. We go out and talk to with this condition. A standard deviation of $10. The distribution is slightly skewed to the right. We go and talk to try to think. I want a good number right here. Give me a second. I can't think of the number in my head. I've almost got it. Is that right? Is that right? I'm getting so bad at these numbers. Okay, let's go with that. Wait one more second. That's right. 225 students. And find a of find a mean of no, Darius. Find a mean of. I'm doing the math in my head right now and figuring out what I want this answer to be. We find a mean of. Yeah, good. Yeah. Okay. So here we go. Be careful. A lot of people make mistakes on this. 1. Do we meet the conditions? Okay. 2. What is the mean of the sampling distribution? 3. What is the SD of the sampling distribution? 4. Draw the sampling distribution. 5. What is the sample? 6. Is this on? Give numeric justification. Okay. What is the first condition right here? First condition, and do we meet it? Who's got me on this? Try to solve this right now. What is the first condition, and do we meet it? Condition 1, what? Do we meet it? What is the first condition, and do we meet it? First condition, and do we meet it? Do we meet the condition? Do we meet the condition? Yes or no? Do we meet it? Do we meet the condition? Nope. Good answer. It was not a random sample. I'll change it. We spoke to students from Brown Hall. We speak to 225 random students. We can't just go to one residence hall and speak to 225 students from that residence hall. That's not a random sample. That would be like a convenience sample or attempt to cluster at location. It's a non-random sample. You want to make sure when you're cluster sampling that they're random. You don't just go to one place and select everybody unless that one place would be random location at the campus that people would attend. Don't want to get too much into the sampling methods here, but now it's random. It is met because it says it's random. Condition 2, and why do we meet it? This one's a little more vague, and you have to think through it. Condition 2 is what, and why do we meet it or not meet it? What is condition 2? First one is random. We took a random sample of 225 students. We meet the condition of random sample. What's the next condition? It is less than 10%. And do we meet it? Do we meet it? It's met, and why? Give me, David, good to see you there. We meet it, and why? Give me numeric justification. So this one you do have to think a little bit theoretically and have to know some outside information for. But give me what? Why do we meet it? You always have to think n divided by capital N. This problem does not give capital N. And there it is right there. So exactly. And yeah, it depends on how you think through it. It doesn't even say UT students, right? So yeah, exactly. And Riley said too, great job, Riley, and everybody. As long as you assume n is larger than this, you're good to go. And you just divide the numbers, and it has to be less than 10%. So it's really, if I were to say we want to understand UT and we sampled 20,000 students, that would be more than 10% of the UT population. About 4,000 is more than 10%, 3,000 to 4,000 in that range, because we're like 30, 40,000 students. We're in that. Depends if you count graduate students and things. But this is not more than 10% of the population, so we are good. The less than 10% condition is that you sample less than 10% of the population. Now, what do you do before you say the next condition here? What are you going to do before you say the next condition? What are you going to do? Because I know what you want to say. You might even say that you put those pause in the chat. Okay, so what's the next condition? We're asking people, how much money do you spend on your meal plan? The question people are asked is, how much money do you spend on your meal plan? You have to look at the question asked, and it's quantitative. So what's the next condition? It's quantitative. So that's not quite a condition. It's just like, okay, so it's quantitative. So which condition do we do? Large enough, and Riley points in the chat. Large enough sample size. Step 1, check the shape of the distribution. Check the shape. And we got normal, skew, very skew. I'm running extreme skew. very skewed. Normal, skewed, or very skewed. So this one says it's slightly skewed, right? Know the requirement. And the requirements are, there you go, Norm. 1, 25, 100. And then is our n large enough? So do you think we pass this condition, yes or no? Do we pass this condition, yes or no? So it says check the shape. Well, the shape of it is slightly skewed to the right. So if it's skewed, we need a sample size of at least 25. So our sample size is 225. Is our sample size of 225 at least 25? So you want to mark all the notation, and you have to say, since it's skewed, these are the requirements. If it is skewed, you need at least 25. If it's very skewed, you need at least 100. If it's normal, you can just have 1. So the question becomes, is our sample size of 225 large enough? Is this n larger than the requirement? Because that's the requirements. So the requirements, and I tried to line them up right here where normal is 1, skewed is 25, very skewed. So the more skewed it is, the larger n needs to be. So is our sample size large enough, Dylan? Yeah. And what this is this is the central limit theorem. Like imagine I told you in this question, we're only taking samples of 2, and the population is very skewed. If the population is very skewed, and we only take samples of 2, is n large enough? Everyone in the chat, if we only take samples of 2 and it's a very skewed population, is n large enough? So would n be large enough if we only take samples of 2? No. And here you go. Still skewed. If we do not meet the conditions, and write down this note, the distribution won't be what? If we don't meet the conditions, Jackson, that is correct. Those are the numbers to memorize. 1 if it's normal, 25 if it's skewed, and 100 if it's very skewed. If we don't meet the conditions, the distribution down below will not be what? Which is the sampling distribution of sample size of means 2. Because we're taking 10 observations and finding the mean of that. Taking 10 observations, find the mean of it. If we don't meet the conditions, it's not normal. You see, it still has a little bit of skew. As you go towards 25, I guess this is just skewed. It becomes more normal and tighter by a factor of square root of n, and the mean stays the same. The mean doesn't change. So the reason to meet these conditions right here, all 3 of them, is to have a normal sampling distribution, to use rules like the empirical rule, 68, 95, 99.7. So what is the mean of the sampling distribution? Who knows what the mean of the sampling distribution is? This one's super easy if you know the notation. It says, what is the mean of the sampling distribution? What is mu y bar? So what is the answer for this one? What is mu y bar? It says, well, what is mu y bar? If you know how to solve this one's like, psh, Brian, come on. What is mu y bar? Close, Douglas. Good try, good try. We know that the average student spends $60. So it's going to be 60 right there. And that's because this is going to be mu. And so that's going to be mu, and it's going to be $60. So it's from the truth. So that is mu y bar. It's the expected, what we'd expect to see in a sample. Like, if you know the average student spends $60, well, you'd expect to see in a sample student spending $60. Next, we have, what is the standard deviation of the sampling distribution? So the standard deviation is going to be sigma over square root of n s d y bar. So what is this equal to? No worries, Douglas. You're doing great, man. You're here practicing. You take those wrong answers out of your head, you throw them away. Say.
Wow.
Who knows this one? I want to see if my math was correct. Yep, that's what I got. I cheated with perfect. For some reason, I couldn't do 15 times 15 in my head. I doubted myself, and I checked it, and I got it right. Because we know the standard deviation up there. So this is equal to 10 over 15, which is equal to repeating. And then draw the sampling distribution. Let me ask you right now really quickly. Is 66 weird to see in this sample? Yes or no in the chat. I want everyone to respond, or you can click the button. Is 66 weird to see in this sample? I didn't hit the poll yet. Is 66 weird to see in this sample, yes or no? Was 66 weird to see? What do you think, yes or no? And this is where, don't worry, like I'm looking at, we might have a lot of people watching because it's like decimals on the, so if you draw the sampling distribution, the answer becomes apparent. Because when we draw the sampling distribution, we put the mean at the center, and then you go up standard deviations. And you get 60.66, 61.33, 62. Where is 66? Someone say it in the chat. Where is 66 on? Where's 66? You see, because we're going up the standard deviation. So that is the standard deviation of y bar is equal to 0.66. So that's how much we're going up each time. It's way off the curve. It's way off the curve. What is the z-score of 0.66? It's beyond the third standard deviation. Exactly, Doug. It's way off the curve. And then the mean for the distribution of the sample proportion is equal to 60. And you can see that right here. There's where 60 is at. That's why it's the mean of the sampling distribution right there. The mean of the distribution of the sample, the mean of the distribution of the sample mean. So what is the sample mean? That's just what y bar is. The question stated that y bar is equal to $66. And so with y bar being equal to $66, you then go into here and you figure out if 66 is odd, which is z-score of y bar is equal to y bar minus mu over sigma over square root of n, which is going to be 66 minus 60 over 0.66, which is going to be equal to, I believe, 6. Right there. Is that right? No, it's going to be equal to 9. I think it's 9. Yeah, it's equal to 9. So 66 minus 60, of course, and then divide by, there we go, 9. Does that make sense to everybody right there? It's way off the curve. A lot of people will use the original standard deviation. The big problem is this down here. This is where all the mistakes occur. Because what everyone does is they constantly use the original standard deviation. They don't do sigma over square root of n. They just take the original standard deviation and just divide by it, but that's not the standard deviation for the, so they just divide by sigma, and then they say, oh, this isn't odd because I divide by 10 and I get 0.6. It's such that, like, sometimes I wonder if anyone knows the chapter. Oh, like, no one does it right. It's that the standard deviation, because the central limit theorem says two things: that the distribution of the mean will get more water and water. The central limit theorem states two things: that the distribution of the mean will get water and water. So this is the original distribution up here, but when we take samples of size 5 and look at its distribution, the new distribution is more water and water. The new distribution is more water and water. The new distribution, according to the central limit theorem, kind of as sample size increases, the distribution will become more what and water. Trying to, dang it. Normal, it'll become more normal in what else? It'll become more normal in what? If I run this simulation a whole bunch of times, what will the mean be down here? Tighter and normal, exactly, Darius. If I run this simulation a whole bunch of times, what will the mean be down here? What will the mean be? So this is the new distribution of the sampling distribution of what we get for sample size 5s. If I run this simulation a whole bunch of times, what will the mean be? What will the mean be? If I run it a whole bunch of times, what will the mean be? The mean will be the same. William on fire right there. The mean will be the same. It'll be 10.28. Now, I've only done a few simulations here. what will the standard deviation be? Let me change it to 25, make it easy. What will the standard deviation be now? The mean will be the same. The mean is not dictated by sample size. The mean stays the same. The mean stays the same. So if I run this, the mean is going to be the same. I'll run more simulations, but the mean is going to be the same value. What is the standard deviation going to be with more simulations? I'm increasing simulations. Sarah, good to see you there. Good luck, everybody. What will the standard deviation be? And I did a trick because the original one is 5, and I'm taking samples of size 25. So people are right that when you look at this, the mean doesn't change. It does get smaller. So the mean down here is going to be, I'll write it in blue. This is mu y bar equals mu, and mu is this value up there. So this is going to become 10.28 because the simulation will do that. The standard deviation is currently 5, but the new standard deviation, we need to do more simulations like law of large numbers, chapter 10, I believe. Actually, I think it's chapter 10. We need to do more simulations because this is sigma, and the new standard deviation down here is sigma over square root of n. So what will the new standard deviation be if we continue this simulation? If we continue the simulation, this will change and become what? What will it become? Because it was originally 5, and then we look at the sample size over here, over the new standard deviation according to the simulation will become what? Well, that's the answer right there in red. The new standard deviation, which is, this is going to be the standard deviation of y bar, that's what that is equal to, is going to get smaller, but what is the exact number it'll be? It'll turn out to be exactly what? Because we can do the math to figure out what it'll be. If we continue this simulation to see what the truth is, it's going to turn into what value? Well, that's what it currently is with a very low run of the simulation. We haven't simulated enough. Like this is law of large numbers. If we keep doing simulations, we'll eventually see what it approaches. So we need to keep doing the simulation, but what's it going to turn into if we keep doing the simulation? The answer is the math. It's sigma over square root of n. So what will that be? I made the math easy. It's 5 over square root of 25. So if we keep doing the simulation, it'll become 1 because it's 5 over 5 because 5 over square root of 25. And then the shape of this will start to look more what? The shape of this, great job, Darius, right there. The shape of this will start to look more what? If we continue the simulation, we have kind of a large enough n right here. It's going to start to look normal. And watch this. We go right here and look at this. Do you see how the simulation shows that we might have a bit of a large enough n? The standard deviation is now 1, and the mean is this. And this is, the simulation is just showing us what the sampling distribution looks like. And yeah, the standard deviation is 1. You can solve any of these out, especially when you do 5 as the standard deviation. That's really easy. But if you do this right here, you could say, well, the new mean is going to be 15.65 for the lower distribution. And the new standard deviation, you take 8.25 divided by square root of 25. 8.25 divided by square root of 25 is this. So 1.65, and you run it, and you get 1.65 down here. So we are literally able to tell what will happen. Does this make sense, Riley? And then it looks more normal. So because the central limit theorem states that the distribution will get tighter, i.e. sigma divided by square root of n, and the distribution will get more normal. And this is not the original distribution, which is up here at the top. It's the distribution of the sample mean, of theoretically what we could get in a sample. So you would say, well, this is a theoretical sample. Yeah, it's great to know exactly. And this is what large enough n is doing, is it's saying, is our n large enough that the distribution of the sample mean will be nearly normal? Well, we'll be back here for some office hours in the afternoon. How are people doing? How are people feeling? Go to the main screen. Really good job. I'm very proud of everybody. I feel like my chair was moved today. I'm like, did someone come to my office and got fuzz on me? Fuzz on me? Whew. It's going to be a busy, busy week. Nervous about it? Yeah, it's practice, practice, practice. And I really mean that. Like, the more you practice, the better you'll do. I really think practice pays off. I got interviewing, filming something? What's going on? Interviewing, filming. Where'd it go? I don't even know where that went. I think I just hallucinated something. Oh, wait. Is it? Go ahead. Let's see. How does Friday sound? Oh wait, Friday I'm busy. Yep, in-person office hours. Swing by in-person office hours today. Yep, we just did chapter 14. We could probably do that later today to do the full homework quiz stuff. Yeah, exactly. Darius is on fire right there. It's Friday. Should I do... Let me email them and say, how does Wednesday morning-ish or Friday morning-ish look/sound? Okay. Oh, it's Mike Wise. Oh my gosh. Well, we're going to have office hours here in a moment. These were kind of impromptu office hours. With that, I got 49 emails right now. I'll let everyone go. Bye for now, everyone. Bye.